Welcome to this talk. I'll talk about bringing the neural search paradigm shift to production. So my name is Jo Kristian Bergum, and I work at Yahoo. I work at the Vespa team here in Trondheim, Norway. And in this talk, I'll talk about the neural search paradigm shift and what I mean by that. I'll talk a little bit about transformers and BERT and how not to use BERT for search ranking. I'll also touch on how to use them for search ranking. Quick introduction to Vespa, the overall introduction to Vespa, and a few slides on Vespa at Yahoo, and the scale we operate Vespa at Yahoo. Then I'll talk about representing text, sparse and dense representations of text, and how to do efficient retrieval over those representations. Then I'll talk about the ranking framework in Vespa, and finally I'll touch on a sample application that we have built, an open source sample application, which you can use to produce almost state-of-the-art ranking runs for the MS Marco passage ranking. So the neural search paradigm shift. So BERT, the bidirectional encoder representations from transformers, was released by Google in late 2018. And this kicked off a BERT revolution. In January 2019, researchers applied BERT to MS Marco passage ranking data set. And the effectiveness basically increased about 30% from the previous state of the art in 1 week. So that's almost unheard of when you look at various benchmarks, when you suddenly have that kind of gap from the previous state of the art. For those that are not familiar with MS Marco and the MS Marco dataset, so the MS Marco dataset is by far the largest data-intensive relevancy collection that is in the open. It has about 500,000 queries, and each of the queries have annotated with a relevant passage. There's also a document ranking variant of the MS Marco dataset. And the great thing about this open large dataset is that researchers and industry practitioners can evaluate their ranking models and validate how they compare to the current state of the art, so that you get to actually be able to say that, is this a good ranking method or is it a bad ranking method? So I think that's really, really important also in the industry. The metric here is the mean reciprocal rank. It sounds really scary, but it's basically just measuring where in the list the first relevant hit is. So if the relevant hit that is judged by the editor is placed on position 1 by the ranking algorithm, you will have a score of 1 for that query. If it's placed in position 2, it will be 0.5 and so on. And the data set is basically divided into a large training set and a development set and a hidden set, which us, our researchers, don't have access to. And you can submit your ranking runs for the queries in the development set and on the test set, and then you can be listed on the leaderboard. So then after this, in January, there also was a track, which is a relevancy conference where they have used the MS Marco dataset in 2019 and 2020. And in track, they use what we call deep graded relevancy. So in the original dataset, there are very few graded documents per query. In track, there are many per query. So it's a more valid data set because it has a graded relevancy judgments. Editors actually looked at the results, say that this is a perfect relevant hit, this is not so perfect, and this is irrelevant. And for this type of graded relevancy judgments, you use the NDCG metric. And in the graph here, on the y-axis, we see the NDCG, which is the kind of higher is better. And there are 3 different types of models, ranking models here. So the organizers, after people submitted their runs, kind of classified them into 3 different types of models. And the blue is the traditional models using sparse text representation, lexical matching. The red are neural networks, or the previous state of the art, and then there are neural networks based on language models. And as you can see, there's a pretty significant gap between the traditional runs and the models that are based on pre-trained language models. one observation about this relevancy data set is that when you submit a ranking run to this, there's no runtime constraints. So research organizations, they can run ranking models that might take days to produce. So there are no runtime constraints, so they might not be so practical to bring into production. But I'll talk a little bit more about that in the next slides and so on. Yeah, so talked about the paradigm shift, and the paradigm shift, well, it requires some new skills. I think it's really important to understand how these models work and how to actually apply them. And also, this paradigm shift has opened what kind of tools that we use to solve search in quotes. So BERT, I like to demystify BERT a little bit. I won't go into the details of BERT, but I look at it basically as there's a deep neural network architecture, and it has a text tokenizer, and it has a fixed vocabulary. That's how I like to present BERT. I don't dive into the details here of BERT. But the thing with BERT is that the researchers figure out that, how can we build a language model when we have a huge amount of text? How can we build a model? And the way they did this was that they came up with this masked language models. They would take a text sequence, and then they will hide one word in the input, and then they will input it to the language model, and then have the language model predict what the word is. And by doing this on a large corpus, you gain some kind of language understanding, a model of kind of the language. The input here, they have some special characters. There's a fixed vocabulary. You can extend the vocabulary, but it's basically fixed, usually 30,000 unique words in this vocabulary. And there's some special tokens here, in this case, CLS, which stands for the classification token or the start of the sequence token. There's a separator token and so on. But this is the language model. This is the pre-trained weight. So the weights, if you go to Hugging Face and you download a BERT model, you'll get a model that has been tuned for predicting this masked token. So if you want to apply BERT into your domain, let's say text classification, for instance, you need some kind of label data from your domain, from the task specific. And then you could fine tune the weights. You fine tune both basically the whole language model towards the task that you're going to use this language model for. And you need, in order to have BERT to shine on your task, you need that kind of supervised learning. So the pre-training is about using unsupervised large number of text, and then you fine tune it using supervision. Now, how can you apply BERT to ranking? There are at least 3-4 different methods, but it needs supervision. And that's why in the MS Marco dataset, where you have a large amount of graded query and document pairs, where BERT is really shining, because you have a large training dataset. You can use BERT as a classification model where you input the query and the document at the same time to the model, and then you have a classification layer on top of the CLS token, and then you can build a classifier basically classifying, is this document relevant for this query? The other common model that you read a lot about on Medium is using BERT as a representation model. For the representation model, I'll talk a little bit more in depth about it, but then you input document to the model, and you have an embedding representation, for example, from the CLS token, and you input the query independently of the document, and then you have some kind of vector similarity to measure how relevant is the query to the document, or the other way around. But the magic really is in the fine-tuning of the model, and most of the development over the last year, I would say, has been in how we actually train dense retrievers, and how we train BERT, and how we actually improve the training process. Yeah, so I talked about dense representations. So dense representation and using representation learning to learn embed queries and documents into the same embedding space. For example, here in this graph, using the CLS token of the document and the query, and then using some kind of distance metric to compare them. Then you basically have no kind of advanced interaction through the deep neural network. You basically just have a similarity function to measure if the document is relevant to the query or not. However, there's a lot of confusion about BERT, and especially around 2019, summer 2019, when Google, Bing started talking about using BERT for production. All of a sudden, there were a lot of interest in vector search, how to use BERT for ranking. I got emails from Medium all the way, how to use BERT with Elasticsearch and so on. So in October 2020, I had it, and then I had to write an article about it. You can find it on Google. As you can see, negotiations also is not so great here. But what you see is that if you use the pre-trained model, just the masked language model, and you take that and you take the embedding of the CLS token and the CLS embedding of the query, and then use some similarity metric without any fine-tuning for ranking. And you will find a lot of blog posts on Medium using BERT in this way. And it really sucks, because if you compare this on the MS Markle ranking leaderboard here, the researchers from Microsoft, they did actually this. They also was figuring out, how should we use BERT? Google released it. How should we use it? And they tried this approach. And compared to the BM25 that we all know, the lexical matching, the using term statistics and so on, if you compare it, it's really terrible. Like it's 10 times worse. So don't use BERT in this way. I hope this is a key takeaway from, if you don't learn anything else, this should be the takeaway. Don't use BERT, just use the off-the-shelf language model and then take some embedding from that and then have some similarity and then, oh, that's gonna solve my ranking problems. It will not, it will not. So that's really important. So with that introduction, we talked about the neural paradigm shift. We talked about how not to use BERT. I'll now start a little bit about Vespa and what Vespa is. So Vespa, we define Vespa as the open source platform for low latency computations over large evolving data. It's Apache 2.0 license, and you can find it on GitHub. And Vespa allows you to search, filter, and rank both structured and unstructured data. It can handle both dense and sparse representations, scalable in any dimensions, has great support for expressing multi-phase retrieval and ranking. I'll get into that. Supports vector search using HNSW, hierarchical navigable swirl roll graphs, which is a method for doing approximate nearest neighbor search. It has a dynamic sparse pruning algorithm called WAND, and also you can combine these representations in the same query. Tensors, vectors, and so on are first-class citizens in Vespa. Really, it's been for a very long time. So it's not an afterthought. We thought about this for a long time. Supports real-time indexing and true partial updates, where you can update a document value in place, and also elastic content scalability. You don't have to perform any pre-sharding or on your content when you're growing content. So quick history of Vespa for those that don't know Vespa that much. So actually the roots of Vespa goes back way back, all the way back to 1998, when the team here in Trondheim was running alltheweb.com, which was a large web search engine. Then we got acquired by Yahoo in 2003, and Vespa was born in 2004, open sourced in 2017. And in this year, 2021, we launched the Vespa Cloud service. Yeah, so Vespa at Yahoo, the scale we operate Vespa at Yahoo is pretty significant. We serve about 45 billion real-time queries per day. We have it's a hosted service, about 10 production zones across the globe, around 150 different applications, both search and recommendation. I think the largest traffic use cases are around recommendation. Also, we use Vespa for ad serving. Yeah, so you can check out the blog, Vespa AI, for some of the use cases from Yahoo. And Vespa is also available as a cloud service at the Cloud Vespa AI. Quick overview of the architecture of Vespa. So the first distribution, you don't have to build Vespa yourself. We distribute Vespa as RPM packages for CentOS 7. Also Docker, for running with Docker. We have container images, and we also have Vespa Cloud. If you really want to, you can also build Vespa yourself, but we distribute, and we do approximately 4 releases per week of Vespa. And the Vespa application is defined in an application package, where you have your schema, where you define the schemas, where you define your ranking models, and also if you have any plugins, and you also define kind of the serving architecture, how many nodes you're going to use for the stateless container, how many nodes you're going to use for the stateful content cluster, and so on. You take this application package, which has a high-level configuration, you upload it to the Vespa configuration system, which will derive this high-level configuration into the low-level configuration for each of these services in the Vespa cluster. On the top here, there's the Vespa stateless container clusters. So they don't maintain any state. They don't store data. And this is written in Java runtime, so you can deploy your own query functions or document functions or components, linguistics, and you can also do model inference, for instance, query categorization. And the content clusters is where actual stateful, where you actually store and index the data, where you do the model and inference, or you do retrieval and ranking, and you have content and index management. So that's the kind of overview of the Vespa architecture. Similar, you can have distribute the content over multiple nodes, and each of the nodes, the kind of the inside one node, you have tensor stores, HNSW index for vector search. You have inverted index structures. You also have a memory index for fast real-time indexing, and you have a document store, which is the meta of the documents, the actual content of the documents. And there's a transaction log service for fault tolerance, in case there are node failures and so on, that you can replay data structures that haven't been flushed to disk yet. Then you can organize your content cluster in the way of you scaling with data, or scaling with query traffic, or scaling down latency. You can have groups of data, and you can have flat data and multiple groups. So there are different ways to scale the content clusters. So that was the introduction to kind of the serving architecture of Vespa and how to deploy an application in Vespa. Now I'll talk about text representations and retrieval. And yeah, we have a discussion going right now about dense representations for search, and we have sparse representations for search. And there's a lot of interest around dense representations and vector search. So how to represent actually text or queries and documents? There are 2 fundamental ways of doing that. One way is what we call sparse, where you have a very high dimensional vector space, basically the size of the vocabularies, which can get pretty large if you have a multilingual text corpus. But for a given document or a given query, most of the dimensions have a value of 0. They're not present in the document, or they're not present in the query. Then you have another way to represent text, and that is using a dense representation, where you have mapped this sparse representation into a lower dimensional representation on a given configured D dimensionality, and there are very few dimensions that have the value 0. Then there are also multi-dense, where you can represent a document using multiple representations. BERT is a model that does this. And then there are hybrid and dense sparse models. There's a recent paper from Jimmy Lin, where he puts together and combines these kind of different representations. And it's a really nice paper, so I really recommend that. I will make the slides available later on, so you can check out that. Yeah, so sparse representation, here's an example. You have the full dimensionality is the vocabulary. Then you have a document 1, document 2. Most of the dimensions have 0. And as we all know, traditional methods for doing retrieval over sparse representation is using the inverted index. where you have a mapping from a word into a posting list. And to retrieve efficiently over this structure, we have these dynamic pruning algorithms, for instance, block max wand or wand, max score, different algorithms for efficiently find the best documents without ranking all the documents that contain at least one of the query terms. And here comes my postulate number one. A platform without wand is not a search engine. If your platform does not support accelerated retrieval using any of these dynamic pruning algorithms, I will not call your engine a search engine. Then you have dense text representations, where you can use representation learning and to supervise to learn the representations in a dense vector space using the queries and the documents. Using labeled training data, you can come up with a representation where both documents and queries are embedded into the shared embedding space. And retrieval with dense text representations can be done using vector search and a distance metric. So the whole retrieval problem has been collapsed into computing the similarity between a query vector and a document vector. So one of the benefits of this is that you avoid the vocabulary mismatch problem with the sparse representations. If the user didn't really actually enter the same word as in the document, then you might get a mismatch and the relevant document might not be retrieved. And accelerated retrieval with dense representation. So if you want to do an exact nearest neighbor search and you have a large collection, that can be quite costly to bring down the latency because you have to compare a query vector against all the document vectors in your collection. And that is linear with the number of documents. However, approximate nearest neighbor search tries to speed up this by building graph structures or different techniques for doing that so that you don't have to score all the documents in the search for the relevant documents. And there are many methods for approximate nearest neighbor search. Vespa, we use HNSW, like mentioned, and there are different techniques, and some of the techniques are really bad because they have bad recall. And the graph here is from some experiments that I'm doing right now with vector search, where I index 1 billion vectors into one Vespa content node and then measure the recall versus the latency. And this is one of the big benefits of dense retrieval, is that it's really efficient, really strongly sublinear. So you can actually search 1 billion documents on a single node, and you can do that within 5 milliseconds latency. And you can have a pretty good recall about 0.9 using a public available data set. And the second postulate is that a platform without support for approximate nearest neighbor search is not a search engine, because these dense representations are really the state of the art if they are trained right in a domain rich, in a domain where you have training data, and then you can build a really good representation, and it's really fast to evaluate over, given that you use the correct ANN method. There are also supervision that we talked about to actually train representation. You can train representations for both sparse and dense representation. So given the training data, you can learn sparse representations or sparse term weights for sparse retrieval. So we see a lot of development right there, and we see that the sparse method maybe are also catching up with the dense methods. And you learn document and query representations for dense retrieval, typically called the bi-encoder, where you use transformers to encode the queries and the documents. But importantly, you need training data to learn these representations. It's rather unfair to compare unsupervised BM25 against these methods, because you are basically training a representation, while BM25 is really dumb. It has only 2 hyperparameters. So it's, when you compare it, you have to think that BM25 is not trained in any way. But this is from BERT, which is a benchmark for zero-shot evaluation of information retrieval methods. I want you to focus on the green, because on the green row, you have the MS Marco dataset. You have the NGCG score of the BM25 method. You see it's 0.228. Then you have Deep CT, which is a sparse method, Sparta sparse method, Dr. Query sparse method. Then you have some dense method, and higher number is better. And here, except from DPR, you can ignore that. The methods really, they're training and they're improving and they're becoming better. However, if you look at applying those ranking models that has been trained on MS Marco, and then you apply those models to different data sets. So track COVID is a data set, relevance is a data set, natural questions is a data set, different data sets. Then you can see that the average performance comparing to BM25 is actually worse, right? So that means that these dense representations, they don't transfer, they don't have the transfer capabilities. So you apply them to a different model, different data domain, then they might not perform too well. So I think that's really important when people are talking about vectorization models, and you use this model and suddenly your ranking will be great. It might not necessarily beat BM25. However, in domain, it's great. So third postulate, a platform without BM25 is not a search engine. You need somewhere to start. If you don't have training data, you need the BM25, because it's really hard to beat when you don't have a data-rich regime. With low resources, you don't have a lot of click data. BM25 is actually a pretty good sparse way of starting. And if you don't have that in your engine, where should you start? And I think the previous benchmark, the slide demonstrates that, you have to be skeptical about these pre-trained vectorization models because they might not work in your domain. But in one area where dense representations really shine is multimodal representation, and that's becoming very popular. We did a blog post on it lately on OpenClip, which is a joint representation between text and images. And this is our cat, actually. And you can combine these different vectorization models and put them into one kind of feature representation. And this is really hard with sparse representation, because if you embed and learn a joint embedding, and then you can do approximate nearest neighbor search, I think that's really powerful domain. And this is, I think, an area where dense representations really outshines compared to sparse. Now I'll talk about the Vespa ranking framework and retrieval and ranking. So the basic concept is that retrieval is about quickly finding the best documents. It's a retriever that you actually can calculate, because it has a very simplistic scoring function that it actually can be applied cost efficiently over potentially billions of documents. Then you have stages of re-ranking stages, which are applied on a smaller subset. And in Vespa, we have this kind of separation between the query formulation, which is we call the physical retriever, is actually where you express, how I'm going to retrieve documents. And there are 2 ways or 3 ways to do that efficiently with Vespa. It's the sparse, the weekend methods, and dense with approximate nearest neighbor search. And you can also combine these methods. So that's the kind of how to do efficient retrieval over large data set without running out of budget or cost. Then you have ranking expressions where you have actually configurable, much more flexible ranking, where you have access to models, features, and so on, and you can decide your own ranking functions, or you can use some machine learned functions. But the retrievers, they need to be efficient. If in case that you're operating on billions of documents, then they need to be highly efficient. If you have a very low document volume, you might have a sophisticated ranking model which actually applies on all documents. You don't have to have this kind of retrieval fast stage. The 2 efficient sparse retriever implementations is Vespa. There's one that we call Weekend, which operates on text, where you can have linguistics, TF, IDF, results, integrates with linguistics and stemming and so on. And then you have the wand query operator, where you as a user specify the document side weights and the query weights. So you have full control over the weighting. And this query operator is great for example, using learned sparse representations, where you can, for example, use the BERT sub-word vocabulary IDs to represent in the document with the learned sparse weights, and similar in the query. Yeah, on the dense retriever, you have the nearest neighbor search query operator, where you can enable HNSW indexing, so that we're using the approximate version. You can switch between using approximate and exact, so you can compare the vector recall, different distance metrics, Euclidean, angular, also bitwise Hamming. And you can also control the tensor or the vector cell precision. So you can have a vector of float or vector of B float, or you can have a vector of integer 8. So you can use different resolutions. And this is really important, because then you can have more data per node without running into memory issues. The Vespa HNSW supports all the kind of real-time updates, like the inverted index structure. So you can do delete, update, and add and instantly, and to have it indexed within the same kind of sub-millisecond latency that you have with the Vespa inverted index. And this is how you actually interact with Vespa on the query side. You have this Vespa query language, YQL, and you can express, in this case, we are combining both sparse and dense retrieval in the same query. And we're also passing a tensor, embedding tensor with the query, and we have the use query, and we're using wand for the sparse representation, and we're using approximate nearest neighbor search for a dense representation. And then you have a ranking profile where we get to. But real world is constrained, and you also have things like diversity, and the same query as above, but you want to have some kind of filtering. You have visible equals true, category contains sports, etc. And then you can do grouping, and you can diversify the result set. And this diversification, the Vespa grouping framework, also works on sparse or dense retrieval. It doesn't care. And I did actually a blog post on this recently, so you'll find that on the blog site if you are interested in that. Ranking with Vespa. So we talked about retrieval, how you actually express ranking in Vespa, and that's configured in the document schemas. We compile these expressions, ranking expressions, using LLVM, and we use it into the C++ runtime. And you can write expressions like this. Here you have a BM25 ranking feature of a field text, and then you combine it and read the value of a document only attribute called docCTR, and then you have a tensor product. There's a rich set of built-in text ranking features, examples, BM25, native field match, all kinds of text matching features. And you don't need to kind of change the query formulation, adding should, or like in Elasticsearch, you have to manipulate the query tree to get different boosts from the inverted index structures. You can just change the ranking expression, and you can redeploy, and it's a live change. It's also very easy to express multi-phased ranking. I'll get to that. And tensors are first-class citizens in Vespa. We started with tensors to represent them in the Vespa document model in, I think it was 2013. And you can have tensors in queries and documents, and also what we call global documents. And here's some examples of defining tensor fields, both in the query and in the document. And we call, like, more or less in Vespa, we call it a tensor feature store, because you can access these tensors in ranking, and you can combine them with queries, and you can also combine them with what we call global documents that are present on all the content nodes. Then you have the tensor computation engine, where you can do, here's an example of a tensor product, and we do recognize these recognize the expressions, and if possible, we hardware accelerate them using special CPU instructions if possible. And models, we did a big bet on Onyx, which is the Open Neural Network Exchange, where you can train a model in your favorite framework like PyTorch, TensorFlow, and so on. And then you can export it into the ONX graph format. Then you can import that to Vespa. We've been running GPT models for a long time, spent a lot of time optimizing GPT expressions. We integrate with XGBoost and LightGBM, so you can train those classic learning to rank models, import them into Vespa, and then have Vespa evaluate the GPT model. You also have ability to run model inference with ONX runtime, and you can run this on the stateless container cluster that we had on the top, and you can also run it on a per document basis on the content clusters. There's no model to rule them all. So this is from a paper from Baidu, pre-trained language models for web scale retrieval. A lot of boxes because they're combining both sparse and dense representations. They have some feature database, embedding base. So it's not about just using one type of model. If you read that paper, you'll see that they're both using GPT. They're also using neural ranking, and they're making this in several stages. So it's really easy to express these type of models in Vespa because you don't have to call out the different services. You can express them here. Here's a ranking profile, which using the result of a query classification model, which is run on the stateless layer, which calculates a dot product score between the most probable query intents along with the most probably document categories on the document side. There's ONX model evaluation, and there's in the first phase there's a LightGBM, which is a GPT family ranker, and in the second phase you can have basically an ensemble of ONX, which is a neural ranker, and a query categorization model, and the intent score. So you have this kind of ensemble of models. So it's really easy to kind of express this into one engine because it integrates with these models and put them into the same kind of framework. And this is a slide that I did for Twitter. So comparing what Vespa can actually do in one engine compared to running search in the wild is that typically services, when we talk them, they have some vector search library, for instance, Feist, and they have an inverted index library, maybe Lucene, maybe Elasticsearch, maybe Apache Solar. They have some GPT, maybe some TensorFlow model servers. Then they have the document storage, embedding storage, and you have to combine all of this. And this is the kind of architecture that we try to replace, and instead have Vespa serve that as an end-to-end platform. So some details on ranking with transformers in Vespa. Scaling transformers for production. So BERT seems really expensive, you know, how to use it, what's your latency SLA. There are a couple of great things about when you want to use a transformer for ranking. You can choose the model, how you if you're going to use distillation, quantization, so different techniques, and also this trick that the query typically is shorter than the document, which is great for these embedding models because offline you're producing the documents with a longer sequence length, but at the runtime you're operating on a relatively short query. And the best way to scale BERT is not using BERT, instead using a smaller, more with the same accuracy model. So this is a comparison of different types of transformer models. So BERT is the base model BERT. If you look here, the average accuracy on different NLP tasks, it has 109 million parameters. But Microsoft released some distilled versions. They have the same accuracy, but they are, if you use them with quantization, they are 27 times less cost. That basically means 25 times less latency as well. So if you want to use BERT for production, please think about not using BERT and instead using one of these smaller models. And that's what we did for when we did a submission to them as Barcode passage ranking. If you remember previous slide, the first slides, I talked about a mean reciprocal rank of score of 0.35. Here, using Vespa in the second here, we have a ranking run producing a 0.4. And this end-to-end represented in Vespa in a serving engine where you can come in, write your query in the web interface, and then have your results, and you have end-to-end pipeline in 100 milliseconds. And this is a combination of dense retriever, BERT, and finally a late interaction. No, sorry, not late interaction, but a full interaction model. This is the kind of application package, the document passage, text, which is actual passage text. Then you have the BERT token IDs. You have the embedding field, which is used for dense retrieval. And then you have another tensor field, which you use for this BERT model. So, and here is the transformers, how to actually represent these. And these are available as an open source sample application. And I think this demonstrates that with Vespa, you can have this end-to-end represented and have close to state-of-the-art retrieval and ranking. And with a relatively low cost. We're talking here that you can actually do this in 100 milliseconds. And we're even in this multi-phase retrieval and ranking pipeline, we're actually beating like large models with 3 billion parameters just by having this smart multi-phase retrieval and ranking pipeline. This is the architecture. So this is similar where you have both inverted index, HNSW index for dense retrieval. You have these local ranking phases, and then you return the results, and then you can have optional re-ranking or optional diversification. And in this application package, there's also small snippets of Java code to bring all the pieces together, because this sample application has the option of both using sparse or dense or hybrid combinations and different ranking models. So it's like one application to demonstrate a lot of different ranking techniques, because as you've seen, you need to have ability to both use WAND, BM25, dense retrieval. You need all those capabilities in a modern search engine. And that was my talk. And if you hated it, you can tweet me at Jo Bergum. I'm active on Twitter, and I'm open for Q&A and some discussion. I hope to have a lot of questions from you.
Does the query type affect if we use like BM25 or dense retrieval? I mean, sometimes you have like just keywords as a query, and sometimes you have like a full sentence. Does that affect what we choose, if we choose a BM25 or dense retrieval?
Right. Yeah, it's a good question. So my point about dense retrievers is that if you're considering using dense retrieval, using vector search, you should use a model that actually been fine-tuned for your domain. So I think that's really important. And if your online example query has a different kind of distribution than it was trained on, then I would not use a vector search to solve that problem. Then I would use like a traditional weekend query and BM25. So the point is that of these dense retrievers is that if they're trained and you have data and you can train them, they're great, but they don't generalize that well. So if you pull a model from someone that says that, hey, this is a great vectorization model, it might not be great for your domain. So if that model was not trained on sentence length queries, it might have very poor results.
Great talk first. Thank you very much for taking the question. I wanted to ask you, what was the most surprising thing that you experienced while experimenting with neural network?
Yeah.
In this call. Yeah.
This is a really great question. So we decided. So we looked in 2019. We saw that BERT really rocketed on this MS Marco leaderboard. Right. We saw that all the research community was like diving in. This was even prior to Hugging Face. You know how to get hold of this model. It was hosted on some GitHub of Google, and then all these Medium blog posts, BERT as a service, and the biggest surprise to me was that we also struggled, how do we actually use BERT? So we also started to look at, oh, it's going to use as a representation model. People are suggesting it to using like this. But we knew BM25, and then we could basically look at some benchmarks and we were like, hey, this is cool. It's vector search and we're doing great. But if you compare the results to BM25, they really suck. And I was like, this is not working out for us. And that was a surprise because people are promising this neural search. And then in 2020, researchers from Facebook with the dense passive retriever paper, basically, how to train the retriever. And that started really the revolution on how to do dense retrieval. I think that for me was the biggest surprise, that there was so much misleading information about how to use BERT. And so for me, that's a key takeaway. And that's why I also talk a lot about this, because I know that when I have this experience, I know that there are others out there that will have the same experience. So that's one of my key points. So that's been the biggest surprise. The other surprise has been that we were able to beat these large 3 billion parameter T5 models using this ranking pipeline, using this smaller BERT model from Microsoft, and that we can run them on CPU, end-to-end retrieval, representing the Vespa, and have an end-to-end response in a serving system in 100 milliseconds. When we started that journey of getting vector search, getting the ability to run BERT in Vespa, we were thinking, how we will never be up there in the state of the art. We will never be close, but we should do better than BM25. And that we actually reached that milestone this year, that was also a huge surprise. So that's something I'm really proud of.
Thank you very much.
Okay, so the next question is from Dimitri. So let me unmute you.
Yeah, thanks, Jo Kristian. So my question is, if you experimented with non-NLP models like CLIP, and do you have like similar research as you've shown on the BERT models table for like image or speech, or do you have plans to research these models in the future?
Yeah, that's a great question, Dimitri. Thank you. We actually did a blog post, two blog posts, to release 2 new sample applications on using OpenClip, which OpenClip is a joint multimodal where you represent both text and images in the same embedding space. So it's been trained with both image data and text data, because you have these large data sets where you have the image, then you have some textual description, and then you can assume that that textual description is about the image. And these models are really interesting, because then you can do a text query, and then you can retrieve using approximate nearest neighbor search, and in this joint embedding. So you don't have to produce an image and do reverse image search, but you can actually do a textual description. So yeah, we have played with CLIP, and there are 2 sample applications actually out there. And if you check out the blog Vespa AI, you will see a write-up, and you can reproduce this yourself using Vespa. So, and also it includes a video where we use take a video sequence and we encode frames using this OpenClip model, put them into Vespa, then you run your query, then we retrieve using approximate nearest neighbor search, and then we use the Vespa grouping framework to aggregate from a photo score in the video into a video score. So that's a powerful feature of Vespa, that you can combine nearest neighbor search with Vespa grouping on top of that, and then have an aggregated score. Yeah.
Yeah, thank you. That was quite comprehensive. So if you could share the link to that blog post, that would be also great.
Yeah.
Thanks.
Brilliant. Okay, so we have one last question from Svein. Let me unmute you.
Hi there. Thanks for the talk. So what I'm thinking is, for the use cases where you've been deploying semantic search within Yahoo, two use cases where we previously used text search, but now they're starting to use this hybrid between semantic search and text search. How relevant are the how relevant do you see text search going forward as semantic search improves?
Right.
Yeah,
it's a great question. I think personally, when I talk about semantic search or dense retrievers where you represent queries and documents in this embedding space and you use these similarity functions, what's demonstrated on open benchmarks is that these are great first phase retrievers. They are fast and they retrieve the relevant documents, given that they have been fine-tuned on the domain. So in that sense, I think that dense retrievers in the data-rich domain will replace sparse, WAND, and those representation. But in the re-ranking phases, still exact matching is valuable. So I'm not sure if sparse and this text representation is completely going away. I don't think so. I think you still need that because, and that's what I've been talking about in this, that we have in Vespa, you have the traditional methods and you have the new methods. And if you have in your domain, you don't have a lot of data, then you can start off with BM25. You don't need different technologies to solve that. Yeah. And I don't think that vector search alone, and that's demonstrated as well on MS Marco, that vector search alone is not giving the best result. The best results are using a dense retriever and then re-ranking using a more advanced model with full interaction between the query and the document. So I don't think that vector search is great for end-to-end ranking. It could be used at that, but we see these later stages adjusting and re-ranking the dense retriever. Yeah, I think that's. There's also an interesting paper from Facebook recently to joint learn how actually embed the sparseness into the dense representation. So that's interesting because when you look at some data sets, the overlap between these two methods are not great. So they're complementary. If you have a very specific phrase in your query, you want to have that exact match, right? And I think this has been brought up before. If someone actually goes typing in a phrase in a search engine, you expect the search engine to actually search for that phrase, not use some kind of semantic vector representation. So I don't think that dense representations will automatically replace sparse immediately, no.
Yeah, okay. This matches also what we've seen at Spotify with our use case. Yeah. Thanks.
Thank you.
So, Jo, how much time do you have for how many more questions?
Yeah,
we have.
I love it.
Okay. Do we have time for?
Yeah.
Because we have Antonio. Then okay. So the next question is from Antonio. Antonio, you can unmute yourself.
Hey, Jo, great talk. So I had just a quick question about the comparison in terms of like efficiency and scalability between inverted index and ANN-based approaches. Basically, what I'm wondering is with inverted index, you can still rely on sharding and document reordering, a bunch of techniques that can improve the latency of your queries.
Yep.
How do ANN-based approaches behave when like the number of documents, for example, reach the order of like tens of billions? And how do you deal with that with Vespa?
Yeah, so that's a great question. So obviously Vespa handles where you can actually distribute the content over multiple nodes. There are some challenges there around using approximate nearest neighbor search and algorithms like HNSW. And I'm doing a blog post series on that right now, which where we are writing about billion scale vector search with Vespa and the various trade-offs around that, especially around distributed search in using a vector search. So I think that's and there's a paper called SPAN from Microsoft, what was released 1 month ago. And we have basically taken that paper and inspired by that paper, have a GitHub issue in it when we actually realized that on Vespa. And that technique is really great because it allows much better distributed scaling. Regarding sparse, dynamic scoring, WAND versus approximate nearest neighbor search, they have their own properties, but I think in general that the approximate nearest neighbor search with HNSW gives a really good performance. Like we put 1 billion documents on this data set into one Vespa content node, and you can do that with 5 milliseconds. I think that WAND will struggle with queries that have posting lists of size 1 billion.
Yeah, okay, thanks.
Okay, so the next question is from Zenit. Zenit, you should be able now to unmute and ask the question.
Sorry, I have a bit patchy connection. If you can't hear me, let me know. So like and sorry also if I missed this one. So how do you incorporate like non-textual signals like popularity, like for movie search or other features like distance from user for hotel search in the context of neural search?
Right.
Like, for example, like if somebody enters Lord, it's a good match for some movie called Lord, but usually we would expect Lord of the Rings to be the top result in that context.
Right. It's a great question. So then using the pre-trained language models, and if you look at MS Marco, they are text collections. They don't have a lot of static like you have in real practice. In your domain, you have various statistical features and so on. I had one slide about these multimodal features where the image of the cat and the text, and you had some page rank features and so on. You could, when you're training an embedding model, then you have to train your model yourself. You can use parts from the text representation, and you can use different of the features, so you have those into the vector representation and then have the similarity score. So, but there are things that are difficult to express using vectors. For instance, freshness features, because then you have some decay on the features in the document. Those are the hardest features to incorporate into dense retrievers. Yeah, but it's definitely possible. And in no way, when Bing and Google are using large-scale vector search to do the first phase retrieval in their top tiers, there's no way that they're only looking at the text quality, right? They're using a lot of other signals. But it's all about representation learning, right? So you learn how to actually retrieve in this embedding space. I hope that answered.
Yeah, thank you.
Thank you.
Okay, so we have the last question from Abib. Let me unmute you. And you can now ask your question.
Hi, so I'm pretty new to this and I just need clarification. When you talk about fine-tuning in the domain, are you simply just saying fine-tuning the model on specific data sets, or is there more to fine-tuning in the domain?
Right. Yeah. So if you look at the traditional, if we move away from search ranking, if we look at NLP, if you look at Hugging Face or some of the tutorials, you have the pre-trained model, which is the BERT weights from the weights from the language modeling, and then you fine-tuning, for instance, for a movie data set where you want to classify if the review is positive or negative. Then you tune, giving it labeled examples, and then finally you have a model which has been fine-tuned for classifying if a movie review is positive or negative. So that's kind of the process of the fine-tuning for that, for your specific task or specific domain. Yeah.
Okay. All right, thanks.
Similar for retrieval and ranking, you really need to fine-tune it for either retrieval or re-ranking. and those can have different objectives.
So thank you. So thank you very much, Jo, for your talk, and thank you very much to the audience for all the very interesting questions and your presence tonight. So we hope to go back on site for the next meetup, hopefully, but we're going to keep streaming them. So feel free to join online if you are not in London. So we keep an eye on our Twitter and the meetup group for the slides and the videos and any news from our company. I wish you a good night and see you later. Bye-bye.
Bye-bye.
Bye-bye, everyone.